Hi, this is the next video for Year 2 Mechanics. We're working towards exercise 7C, and we're looking a little bit further at friction and limiting equilibrium. So limiting equilibrium is when the value of friction is at its maximum. Remember, friction can vary between 0 and some maximum value. So friction is at its maximum, so my particle is just about to move, but it's still not actually moving. So limiting equilibrium, friction is equal to mu r, remember that's F max, and also my acceleration is 0. So I'm just at the limit of my equilibrium, just at the limit of my friction. So example 5 really seeks to demonstrate this. It's the maximum force. A mass of 8 kilograms rests on a rough horizontal plane. Remember, rough means there is friction involved. My reaction force and my weight always exist, whether I'm told explicitly or not. The coefficient of friction I'm given, mu is 0.5. Find the magnitude of the maximum force P which acts on this mass without causing it to move if. So, first of all, let's set P horizontally. Remember, friction always opposes motion, and because I want to be in limiting equilibrium, I want the maximum value of P, I can set this straight away to mu r. Okay, so let's resolve vertically. Remember, that means apply Newton's second law. R minus 8g equals 0, so R equals 8g, which is a common sense result. And resolving horizontally, P minus mu r equals 0, so P equals mu r, which is a half of 8g, 39-ish, 39.2 newtons. Okay, if P is not horizontal, let's draw it out again. So 8 kilograms, 8g. Now R will change, of course, and so friction will change, but mu is still a half. P is now at an angle of 60 degrees to the horizontal. So if I decompose P sine 60, P cos 60. Cos 60 is a half, isn't it? So I can write that as P over 2, and sine 60 is root 3 over 2. Okay, same deal again then. Resolve upwards. So I've got R upwards, and I've got P root 3 over 2 minus 8g equals 0. So R plus P root 3 over 2 equals 8g. That's one equation. The other equation comes from resolving horizontally. I've got P cos 60 minus mu r equals 0. So let's put it in the form that the calculator likes. Minus a half r plus P root 3 over 2 equals 0. Simultaneous equations on my calculator. Put that in. So I'm going to go 1 root 3 over 2 and 8 times 9.8 minus a half root 3 over 2 and 0. What do I want? I want to find P, well that's X, which is R, so P now equals 30.2. newtons. So that's example 5. Example 6. What have we got? Got a slope, okay, nice big diagram so that I can annotate it. 20 degrees, a mass 10 kilograms, so 10g. Now it doesn't give me any other forces, so the only force acting down the slope will be the weight, which means it wants to slide down, so I'm going to set my friction to act up the slope. Now I don't know mu, but I do know that I'm in limiting equilibrium, so I can set my friction to mu r. Find the coefficient of friction between the box and the plane. Okay, let's decompose the weight. So 10g cos 20, 10g sine 20, and resolve vertically and horizontally. Resolving vertically will give me r, and I can go straight to r equals 10 cos 20. Resolving up the slope, mu r minus 10g sine 20 equals 0, so mu equals 10g sine 20 over r. Well, that's 10g sine 20 over 10g cos 20. Now look at that, 10g is cancelled out, sine over cos is tan, so I can just write that as tan 20. Make sure I'm in degrees. Tan 20 0.364 to 3SF. I'm actually going to store this to use it later, so store as A. Okay, so I've stored that as A. Now I'm going to look at part B. Okay, this is an interesting one because, well, let's discuss why. So 20 degrees, same particle, 10g, r, friction. Again, I'm in limiting equilibrium. No, do you know what? I'm going to draw it again. 20 degrees, 10g r. Now, we'll discuss why why I haven't put my friction on. In fact, let's put the horizontal force P on. A horizontal force of magnitude P is applied to the box. Now, clearly, my weight is going to need decomposing, and P is going to need decomposing. So let's just do that. So that's 10g sine 20. 10g cos 20 as before. P will go that way and that way, and remember 20 degrees is alternate to that, so P sine 20, P cos 20. Now I'm not told in which direction I'm about to slide, and of course I need to know that to be able to put my friction in the right direction. The question's saying what's the maximum possible value of P? How hard can I push here and yet it still doesn't go up? So if you like, this force is trying to push up the slope, which means friction must be acting down the slope. If that were the minimum, then I'd be just holding it to stop it going down. So the maximum means I'm pushing P, I'm applying as hard a force as I can, and I'm trying to push it up to the slope. That means that friction is acting down the slope. Let's put friction there. Friction, which of course equals mu r. Okay, so resolving vertically, well, I've got this extra force here to be concerned about. R minus P sine 20 minus 10g cos 20 equals 0. So I'll leave that in the form that the calculator wants for simultaneous equations. That's equation number 1. And to resolve up the slope, I've got P cos 20 going up the slope and weight and friction acting down the slope, so minus 10g sine 20 minus mu that I had before, which was 0.364 times by r, and I'm still in equilibrium. Let's put this into the form that the calculator likes. Let's put minus r times 0.364 plus P cos 20 equals 10g sine 20. Remember I stored my answer before as A, so there it is. So if I go back into simultaneous equation mode, two unknowns, these are my equations 1 and 2. Let's put it there, yeah. 1 minus sine 20, I'm already in degrees, and 10 times 9.8 times by cos 20 minus A plus P times cos 20 and 10 times 9.8 times by sine 20 gives me 120 for x, which I've put as r, and 82, which is what the question wanted. Newtons to 3SF. I don't need to write down r, but why not? Okay, have a go at 7C. Let me know if you need anything. See you next time.